Good morning and welcome to another video. In this video, I'm going to go over some calculus problems that are applied, particularly to business applications. I'm going to share my screen at this time. And we're going to go into section 2.2 first. I'm going to check and make sure that it's actually sharing this screen, and it is. Okay, so I'm going to start with, I believe it was question 7 here. This was a hard question that somebody asked. I'm going to bring it up here. So here is your question. It says, a company's, let me just check and make sure that, yes, it is. Okay. It says, a company's total cost in millions of dollars. This is important here. This gets a little tricky later because of the way they ask questions. It's not tricky in doing the problem necessarily, but it's tricky in reading it, because later sometimes they ask you for dollars, sometimes they ask you for million, but this is total cost in millions. This is always given in millions. So your derivative will be in millions per year. This is going to be millions of dollars. The derivative is going to be the change in millions per year, okay? A company's total cost in millions of dollars is given by C of t is equal to 120 minus 70 e to the negative t power, where t is the time in years since the startup date. The graph of C of t is shown to the right. So this graph that they're giving us, notice that starts below 75, has a sharp increase, and then pretty much levels out to flat below 150. We can tell that it levels out to flat around 120, but we'll get to that. Is shown to the right. Find each of the following. The marginal cost, C prime of t, that's just the derivative of this function. So we differentiate each term. The derivative of 120, that's a constant, so that goes to 0. The derivative of negative 70 e to the negative t, that's just slightly tougher. You have the negative 70, so you're going to use that. This is going to be, if I take the derivative here, this is going to be C prime of t is going to equal, I'm going to have negative 70, and then the derivative of e to the negative t power. Well, e is its own derivative, so I'm going to have e to the negative negative t power. But then by the chain rule, I have to differentiate the exponent. So the derivative of negative t with respect to t then is negative 1. So when I simplify this, I end up with C prime of t is equal to, now this negative 1 is going to get multiplied by the negative 70 in the front, which is going to give me positive 70, but I still have the same exponent, which is e to the power of negative t. So my derivative function is positive 70e to the negative t power. And that's what you see in part A, okay? Now part B says, evaluate C prime, which is the thing we just obtained. Evaluate that at 0. Okay, well, if I put 0 in for t here, then I have e to the 0 power. So this becomes c prime at 0 is equal to 70 e to the 0 power. And remember, e is a constant. So when I raise whatever e to the 0 would be, which it happens to be 1, but whatever that was, this is e to the 0 power. Now e to the 0, this is a number to the 0 power, and we know that that's equal to 1. So this is 70. This means that I'm going to have, let me drag this down just a bit. This is going to be c prime of 0 is equal to 70. And e to the 0 is 1. So this is 70. Now, this means $70 million per year, because this is the rate of change. And they have now, this is something that this next question throws off a lot of people, and I'll show you why. If you look here, this is in the box, you have the dollar sign there. You have million after it, okay? So you're going to put 70 in the box because you already have the million. If you look down at part C, it says evaluate C prime at 4, which we're going to do. C prime at 4, but it doesn't have the million. It just has dollar sign and per year. It's missing million. So it says, simplify your answer, round to the nearest 1,000. In other words, the nearest $1,000 as needed. Do not include the dollar sign symbol. They don't want you to put another dollar sign in the box because they already have one there for you. Now, if you evaluate this on your calculator, let's do that. This comes out to, you have, let me see here, clear the drawings. And I'm going to stop sharing temporarily here, and I'm going to do something on my screen. I'm going to bring up my bring it up here from the desktop. Hold on, actually, let me see if I can. No, I don't want to set it up. I want to, yes, finish. Hold on. Technical difficulties, ladies and gentlemen. Okay, so I'm going to bring this up here. I'm going to open it. Okay. Now I'm going to, there it is. Now, I'm going to share my screen here one more time. Let's see. All right. So we have, if you recall, we're looking at C prime of 4. So what I'm going to do is, if you recall, that was 70 E, which is going to be on top of my ln key. So I'm going to do 72nd E to the -4. Be sure you use the minus, the toggle minus down here, and you get that. Now, this 1.282, it says round to the nearest $1,000. This is in millions. This is the trick. So this answer is in millions. $1,000,000. Okay, this is million. So that's $1 million. Okay, now we want dollars. So what we have to do to get dollars, the easiest thing to do is to multiply this number by 1,000,000, and you'll have the number you should enter because this is in millions. So go ahead and multiply here. I'm going to take the number that's on the screen and multiply it. If I can get back to my mouse, there I go. Here I am, and I'm multiplying it by 1 with 6 zeros after it. 1, 2, 3, 4, 5, 6. That, let me clear the drawing. This is my answer, and it wants me to round this to the nearest $1,000. So if I look at this answer now, this is 1,282,094.72. Now it says round it to the nearest 1,000. So if I'm going to round this, I want to know, is this answer closer to 282 million or 283 million? Well, we see that I have a 0 here after the 2. So I have this here. So this is going to stay 1,282,000. Now, I think what most of you entered here was either 1.282, or some of you entered by mistake 1.283. But this is million, okay? This is not dollars. So in dollars, this is what you see written below. So what you want to put in there, we want to round it to the nearest 1,000. So we put in 1,000,000 without the commas for Pearson, 282,000. So 1,282 and then 3 zeros. And that's the answer that Pearson wants. Let me show you. Let me go back. Let me stop sharing this and share the Pearson screen. And you can see that the answer that it took was 1,282,000. And that was why that was the answer that it was. Now, the next two questions have to do with the limits of the original function and the derivative respectively. So the original function is graphed for you. We also have the equation given on top. It says, find the limit as t goes to infinity of c of t. If t is going to 0 in c, then, I'm sorry, if t is going to infinity in c, then e to the negative t, okay, is going to go to 0. Now, why is that? Well, okay, so here, let me annotate this. We can see that as t goes to infinity, it's approaching this line. What's happening to this term, okay? Well, this term, this is negative 70, right? And e to the negative t would probably be easier for you to see if you write this as 1 over e to the t power. Well, if this is e to the t, right, then t is going to infinity. That means this e to the t is getting really large. So this whole fraction is getting really small. So this negative 70 is getting really small. So this whole term is essentially shrinking the more that t grows. The more that t grows, the more this thing as a term as a whole shrinks, goes to 0. So I have 120 in front of it. And I essentially have a term that as t goes to infinity, this thing, this piece goes to 0, essentially. So the whole structure is going to 120. And again, this is in millions, so you can just enter 120 and be safe there. Now, the C prime, if you remember, let me put it back up here. C prime was C prime of t. If you go back to your function that you derived, C prime of t was was 70 e to the negative t. So you're looking at C prime of t. I'm going to write C prime of t, which you see in part A. I'm going to write that as 70 over e to the t power. So this is equal to 70 over e to the t power. Now, okay, so if t is going toward infinity, it's getting infinitely bigger, then this whole bottom part is getting huge, right? And so 70 divided by a huge number makes this number really small. So what happens is this whole term as a term goes to 0. So at some point, and we can see that if you look here, think about the limit of the tangent line here. The tangent line's getting super, super flat, right? Just like the graph does. Here, the tangent line is steep, steep, steep. Here it's steep, but it's flattening out, flattening out. And here it's super flat. It's going to 0. And that's why this particular limit is $0. I hope that helps with that particular problem. Now, there were a couple of more on here that I want to go over. So let me show you those. Let me then get the mouse and move this out of the way. So the next thing I want to go over from here is this number, you got this on your own, number 8. Number 9, the infamous tangent line problem, okay? This actually, we have one that I'm gonna go over that was pretty infamous. This one is actually fairly straightforward. Remember that in general, how a tangent line problem proceeds is first we have to find the derivative of what we're given, okay? So first we want to find g prime of x. So we're going to say g prime of x Now, we have a constant multiplied by e to the negative x. So it's the constant. Remember, e to the negative x is its own derivative. So we're going to write that again. So we have 2, and then we're going to say that this is e to the negative x. And remember that by the chain rule, we're going to differentiate the power that we're doing. So the derivative of negative x is -1. So this derivative becomes -2e to the negative x. So this derivative here, g prime of x, is going to be equal to -2e raised to the power, and I'll write it in, raised to the power of -x. Okay, that's all we have. That's all this is. Now, if you want, you can bring this down for easier substitution. You can write this expression as -2 over, and you can put e to the x below it. So you can say that this is e to the x power, like so. And remember, this expression now, whichever version of it you use, this expression here is the expression, this is the slope of the tangent line. So I need 3 things when I want to write the equation of a tangent line. I need the point, which in this case is given to me as 0,2. So I'm okay there. It's given as 0,2. I need the slope, which comes from substituting into the derivative, which I'm going to do right now. So here I'm going to say that I'm going to plug in my x coordinate, which is 0. So my slope here, I'm going to call this m. M is equal to -2 over e to the 0 power. Now remember, e is a number. So a number to the 0 power, e raised to the 0 power, is going to be 1. So this is simply -2 over 1, which is -2. Okay, so my slope is -2. So I have my point, I have my slope. Now the third thing I need is my b, and there's different ways to go. If you do it this way, you need b. I'm doing it the way that you tend to do it, not the only way there is to do it, but in this case, I need the y-intercept. So I'm going to say that I'm going to plug in for my expression. I'm going to say that I'm plugging it into y equals mx plus b, and I have all my pieces. So my y is the y coordinate of the point they gave me, which is 2. My m is the slope that I just got, which is -2. My x is the x coordinate of the given point, which is 0. And so then I can solve for b. And in this case, I have this equation here. 2 equals, remember, -2 times 0 is 0. So I basically get b equals 2. Now, if b equals 2 and m is -2, then when I go to plug this in, y equals mx plus b, I end up with y, because now I'm writing the equation, m is -2x plus 2. And as you can see, that is my answer, -2x plus 2. Okay, I hope that helps with that piece of the equation. So I'm going to go ahead now and clear my drawings, and we'll go into the next question. I'm going to stop this share for a second and go into the work so I can I will need the calculator, but I need to find the assignment. Okay, so now I have to switch assignments, so bear with me for a minute. Okay, so I want to go into 2.3 here. And we had one humdinger of a doozy problem. Let me review this. So we're on here. This is 2.3 homework. And I believe you asked for some help. I'm not sure with all of the questions. Yes, I'd like to continue. I'm not sure which questions gave you the most problem. I believe we worked this one together. Let me make sure that it's sharing screen. It's not, so let me fix that. Let me stop sharing and share this screen instead. This was this derivative where we had to make this either the x plus 6 quantity to the 1/2 power. So then I had to write 1/2 e to the x plus 6 to the -1/2, and then I had to differentiate the inside of the radical. E to the x is its own derivative, so I have e to the x here. Now 5 ln x was simply the derivative of ln x was 1 over x, so this was 5 over x. This one was a little bit more of a challenge. We went over this already. You should have a solution to this problem here. But it involves, in this case, rather than using the quotient rule, I wrote x to the 9th as x to the -9 and use a product rule, so that when I use a power rule to differentiate this, and the derivative of ln is 1 over x. number 4, pretty straightforward, even though it doesn't look like it. Start with 1 over this amount right here. So we get this at the bottom, and then differentiate what's inside. So the derivative of 2x squared is 4x minus 7. So we got through that okay. And similarly here, this was slightly similar to that, but this was okay. This one was the humdinger of the evening, ladies and gentlemen. So we're going to do that together right now. Find an equation of the line tangent to the graph of x, of f of x, ln x, quantity to the 5th at x equals 6. Now, the other thing is it doesn't want an exact answer. It says round to 2 decimal places. So the answer that we put in was exact and it was wrong. That was my fault. But it was exact and they want it rounded. So I will go through that. Some of what we had was correct, but some of it was not. So let me go through that on the whiteboard. Ln x to the 5th, we have 8 point, okay, so it's 8.59x minus 33.07. Now, I'm going to go ahead and close this now. Close the review because I'm going to go ahead and go over it. And I'm going to share the whiteboard to do it. So, this is what we have. So what I want to do is I want to find, I want to move this out of the way. I want to find, but I want to use black to do it. Okay. So find an equation of the tangent line to f of x equals the quantity of ln x to the 5th power at the point where x equals 6. Now notice, unlike the other equation, unlike the other one that we just did a few minutes ago, they only give me the x coordinate. They don't give me the y. Okay, so if I want to find my remember, when I want to write the equation of the tangent line, okay, I need 3 things. I need the point, which will either be partially or completely given. So if they give you a pair, you don't worry about it. If they give you just an x coordinate, you have to find the y. So the point here they're giving me is 6, but I don't know what the y is, but I can find it because this f of x is like y. So this is like saying y equals ln x to the 5th power. Now, it said don't round anything until the end. So what we're going to do is we're going to write this as y equals, we're going to just write ln 6 to the 5th. Now, the only thing that makes this hard is it gets a little bulky. So my point is actually going to be, for now, it's going to be ln 6. It's going to be 6 with ln 6 raised to the 5th power. That's how I'm going to have to write it for now, okay? And I do need all of these parentheses. These outside parentheses tell me I've got a point. The ones around ln6 tell me that I'm taking the entire logarithm to the 5th power. Okay, my point. Now, the next thing I need is my slope. And we know that the slope comes from the derivative evaluated at x. So we better find our derivative. So let's come over here and let's see. We have y equals ln x raised to the 5th power. The derivative is not all that tricky. So my derivative dy dx or y prime, either way, dy dx is equal to, I'm going to use the power rule here, okay? But this is going to be 5 ln x, okay, raised to the 4th power rule, okay, times the derivative of ln x, which is 1 over x, okay. That's my derivative. Now, that was not where we had a problem. We're going to plug this in at 6. So when x equals 6, we get 5 natural log of 6 raised to the 4th times 1 over 6. Now I can clean this up a bit. I can't clean this up as far as I initially told you, and I'll give you a hint why in a second. This is 5/6 because I'm multiplying this 5 by this 1/6. 5/6, and then I'm going to have to write parenthesis ln 6 to the 4th power. And that ugly expression is, okay, ln 6, this is going to be, let me type that again. This is going to be 5, so my slope is going to be 5/6 ln 6 raised to the 4th power. Now, that was not a problem. The problem was when I tried to bring this down. And now we do have a rule of logs that allows us to do that. Okay, but it only does that if this ln is not part of the parentheses. In other words, if the 4 were only raising the 6, then I could have done it. And that's where I made the mistake. But this is the correct slope. So now my slope is m is equal to 5/6 ln 6 to the 4th power. Now, I have to get b, and this is not going to be the most fun you've ever had. It's going to look ugly, but it's not as bad as it looks, okay? So we're going to start with y equals mx plus b, and keep in mind, I know y is ln 6 raised to the 5th. So this comes from here. This y comes from here. So I'm going to say the following. I'm going to say ln 6 to the 5th power is equal to the slope, which you see on the left, 5/6 ln 6 to the 4th power, okay? Now I have to multiply the slope, so I'm going to put it in brackets. I'm going to put this in brackets, or it's to differentiate it. And I'm multiplying that by 6 by x, right? So this is 6, and then I'm adding b to it. Now, here, right? So I have 5/6 ln 6 to the 4 times 6. These are 3 terms multiplied together. This 6 in the 5/6 cancels with the 6 here. So I end up with the following. I end up with ln 6 to the 5th equals 5 ln 6 to the 4th plus b. Now, all I'm going to do here, and for the same reason that I didn't bring this exponent down in front, I did the first time, that was an error. I'm just going to move this term over, and I'm going to leave b as this. I'm going to leave b as ln 6 to the 5th minus 5 ln 6 to the 4. Okay, so I haven't gotten a decimal approximation. I'm going to, but that's my b. Okay, so what I need to do now, if you remember, let me come back to it. The question wanted us to, let me do something here. I'll show you. I don't know if I took a picture of that one. Let me see if I did. I'm not sure that I did that. Downloads, let's see. I believe not. Let me see if it's in. Or it's on my desktop under documents. Hold on. No. Anyway, what they wanted was, I don't have it, but what they wanted was a decimal approximation. So let me see if I can go back here. Okay, so if we look at, let me just make sure we're not looking at it. I thought maybe we weren't. There it is. They wanted a decimal approximation. So we've done all the work. Okay. we have to get these decimals, 8.59 and 33.07. Now, where do they come from? Well, this is where they come from. If I go up here to the whiteboard, okay, M is 5/6 times ln 6 raised to the 4th power, okay? So pause the video if you need to. Write just this down, and we're going to see, remember, that should be 8.59. We're going to do it together, but write this expression down for M. Now, I'm going to come back here, and I'm going to go to the calculator, and I'm going to say, let's clear this out from before. 5/6 times, oops. Of course, if you put it in wrong, you're going to get a wrong answer, right? So I can either do the times sign, or I can do the parenthesis. Parenthesis is probably easier. ln natural log 6, and we're going to notice here, I'm going to close it twice, once for the argument of ln and once for the natural log itself. Once again, once for the 6 and once for the ln. Raise it to the 4th power, or ln 6, excuse me, let me go back. So this is, my expression was ln 6 to the 4th. So I'm going to do this now. Share my TI, and there it is. And we have 4 here. And we get, sure enough, there it is. 8 point, we want this to 2 decimal places. There's an 8 behind the first. This is 8.59. Okay, that's where that first expression comes from. Now, B is, let's do the second expression here. So the second expression was a lot tougher. The second expression, go ahead and write this whole thing down on your paper for B. ln 6, so B is parenthesis ln 6 to the 5th power minus 5 ln 6 close to the 4th power. Okay, so that's going to look like this. I'm going to go to my calculator here, and I'm going to say ln 6, and I'm going to close twice. I want to raise it to the 5th power. And because I need to move this over, on some calculators, you may not need that arrow. It may drop by itself. If it doesn't, you have to move it. Here, we're actually subtracting, so be careful to use the big subtraction sign. And this is going to be 5. Then ln 6, and we know the drill by now, right? So it's going to be, except I forgot to do it, so I have to go back. I'm going to try and insert a, there it is, ln6, and then I need a parenthesis there, and I need a 4. So it should look like this. And then you get negative 33 point. Now be careful, you only need 2 places. So 0.66 rounds to 0.7. Okay, negative 33.07. And if you come back to the Google answer, you get 8.59x minus 33.07. Okay, I hope that this has been helpful to you, and I look forward to answering more questions in the next video. Thank you very much.